All right, hello everyone. Um, Today we're going to work a little bit on actually being able to write actual assembly code. Um, but before we get started, there's some fixes that we want to do to some things. So I'm going to go ahead and start a branch for that. We will initialize our environment variables and we'll get into our editor. So the first thing is that in the previous video, we had a typo. We had commom compiler flags, and we have something similar with the compiler link flags. So we just need to fix that real quick. And what I can do is I'll go ahead and make sure that we don't have any other um, misspellings of that. It looks like that's the only entry, so we can go ahead and save that, write it out, and then I will go ahead and reuse the commit message from last time. So that's that. The next thing is that I actually want to this is just me nitpicking, but I would like to change the casing for the where tool because it's actually lowercase on disk. So we'll do that. Let's see, this should probably be like rename or, I don't know, correct casing of where tool. In our in our, I think it's the macros file. Yeah. So I don't remember why, but we had this weird making sure that internal wasn't already defined before we defined it as static. I don't see that as being a problem, so I just want to get rid of it just so that it's more in line with what I expect. So that's clean up internal definition. Back in main, I actually want these variables to be called file path. So we'll fix those. And then lastly, I noticed that for this output struct and the read file result, we actually have like different we're using different types, and I feel like they should probably be the same thing. So I'm going to go ahead and change the memory size, which is the content size, to be 32-bit. I can't remember why I chose 16 bits. I don't think that'll be a problem. And then the other thing is, instead of void, I'm just going to go ahead and say it's U8, just because I think that's safe to do, rather than just keep it void. It reminds me though, do we need to I don't think we need to cast it. I guess we can compile, and compile's fine, so that should be okay. So take those two changes and we'll say that we aligned output and read file result types. Sure. Okay, so that was that was the cleanup bits that I wanted to do. So where we left off last time is we had a basically we have a really overcomplicated file copy that if I take a look at our data directory, you notice that I have an input asm, and that's it. And if I were to call assembler and I give it the input file and I tell it where to write it to, so I'll just reuse that same name, output copy. We can see then that the output copy basically has the same contents as what we have as the input. So that's okay, but it's not really, what we need to do. It's not at all what we want. So let's go ahead and make this a little bit better here. What we want to do is we want to write actual assembly code. So I will open up the assembly file. We'll just clean it out. And if you remember from the first video, we had a binary file that we wrote by hand in HXD, and it's 512 bytes long. It has a little bit here at the beginning that's basically going to cause the CPU to spin and basically jump back to this is basically a jump command that says just jump back to the beginning of the jump command. So it's basically an infinite loop. And it has the boot, I can't remember what it's called, boot record sequence or whatever, that tells it that this is a bootable drive. So what we want to be able to do is actually produce a binary file, but have that be produced from assembly that we write. So the easiest way to do this is to use in assembly the db command, which basically means define byte. And what that really says to the assembler is just write out this exact byte at the current location of the output file. So if we take a look here, we need to write, well, okay, so these are hexadecimal values, and that's fine, but let's go ahead and start with something, yeah, that's not what I want. Well, let's go ahead and what we'll do is we will write it out as a decimal number first, and then we'll change it so that we can use either decimal values or hexadecimal values. So if I change calculator as input and I just type E9, we can see that decimal, that's 233. And FD, whoops, it's 253. And FF, of course, is going to be 255. You'll notice that we have a whole bunch of zeros in here. For right now, we're going to write those out all by hand. And then we're going to write the, again, I can't remember the name of it, the special boot sequence indicator. And that should be AA, so that's 170. All right. So we need to fill zeros to be able to produce a 512 byte binary file. So so we have 512 minus 2, so that's 510, minus 3, so that's 507 minus 1, so that would be 506 that we need to paste. So that makes the file a little unwieldy, but you can see that we're correct. The line number right there is 512. And so all we have to do now is update our assembler to be able to take in this file, understand what dB means, and to be able to write out that decimal value to the binary. So let's go ahead and see what that would take. Oh, that didn't work. We want to go to assembler, nope, toolchain, assembler. Okay, so right now we're not really doing anything. We read the file, we get back the result, and we basically construct the output. I don't want to say object, but we have an output struct that we populate, and we then pass that out, and that gets written. What we really want to do is do some work on the contents of the read file. For right now, we're just going to go ahead and do this in main, and it's going to be pretty bad, I'll be honest. But we're just doing it just to push us along just a little bit and make one small forward change. Oh, I guess the one thing that we could have done is we could have deleted not all of that, but we could have deleted this. Okay, so I should have done that as part of the change when we aligned those two structs, which actually was the last commit, so we'll just append that folded in, so like it never happened. All right, what we want to do is we're going to want to take a look here at the contents of the read file result. So let's think about this for a bit. If we have the contents, basically we're going to just hard code it so that we're expecting a dB space and then some number, and then carriage returns. So what we might want to do is while we're not at the end, so what we can do is we'll say, let's go ahead and make new variable, we'll call it at, and we'll say, let's start it off at the read file result contents, and while the value there is not 0, we want to, if we move it along, we can do that, and let's give this a try. If we go ahead and just say we just want to print what that is, except it needs to be that, I believe. Let's see. Oh, what happened here? Print F, format string, type char, but it's an int. Okay. Missing before the end, that's true. Okay, let's take a look and see what this produces. Okay. Yeah, that doesn't work right. But that's okay. Maybe what we'll do is we will let's just deal with writing it once first. This is probably what we should have done in the first place. So you can see here that no, actually that's right. So what this is doing is it's printing out the entirety of the contents, and then we just move forward one character at a time, and it prints out the entirety of the contents again. So that's fine. What we really want to do, though, is we want to say something like if the value at where we're currently at is equal to a D, and the value of this next position is equal to a B, we want to do something. And I think we'll do the same thing for let's see here. It's carriage returns and then line feeds, I think. So we'll do something there. Otherwise, we have something we don't know, and we'll just, I guess, advance that character, and we'll just basically swallow it up. If we get a carriage return and a line feed, we just want to go ahead and move forward those two characters. And then if we get a DB, I guess we can assume there's a space, or we can probably go ahead and just say that it has to be a space like that. So if we do that, and then we print we'll go ahead and just print the character that we're at. So I would expect this to then output just 1, 2, 3, 3. And it doesn't because we didn't compile. So that's because this has to be like that. And this is going to say that it wants it to be a char, so is that wrong? Does that, yeah, okay, that should work. Okay, so it just printed a 2. Okay. So it printed a 2, and then when we looped back around, it basically ate the 3 3s. If we were to do that, then we'll get the 2 3. I don't know why we get 2 2s. Well, that's okay, because we want to go ahead and print now. So what we want to do here is we want to collect the numbers until we get to a carriage return. And we want to, well, maybe what we need to do is know how long that is. So we'll go ahead and say length. Start it out at 0, and we'll say while at length does not equal return, we want to increment length so that's going to tell us how long in characters the number is. So once we know that, what we will want to do is translate each of those values from the character that it is. So in our example, it's going to be the character 2. We want to translate that in to the number 2. And of course for the 3's, we want those to be the number 3. So maybe what we can do is we can say that we have a value. We started at 0. And if we say, we'll just loop until we get to length. And we'll, since we're dealing with decimal for right now, we'll go ahead and for every value we slide over, we need to multiply by 10. And then what we can do is we can say that the value is going to need to be plus with whatever a dot, whatever that is. Now that's character. What we can do is we can do a trick here where we say, because it's going to be the ASCII number that represents the character, the number. And so what we can do is we can say whatever that number is minus the ASCII value of the 0 character, and that will shift those numbers back into 0 through 9. So if we do that, that gives us a value. I guess I should have kept that. And what we can say then at here is we can just go ahead and print out whatever value is. And just to make it clear, we'll just say, you know, your value was blah. Okay, so that didn't work, which is typical, because instead of that, it needs to be the I value here. So there we go. So now we have that 233, but we have it now captured as an unsigned value. And since these are bytes, doesn't really need to be a 32. It could just be a U8, which will go up to 0 to 255. So we have that value now, which is good. Now the problem is we have to figure out how do we actually write this out. We have the value, we want to write it out to the binary file. I'm going to go ahead and delete that output. Copy, and what we're going to start doing now is we'll just do output.bin. So it's not binary yet, but you know we're about to make that transition. So if we have a number, we want to write out whatever that is in binary. Now, I think what we can do is we can just say, we can just set the, we can create some memory for our output space, and we can say that we can just index into it and then just set the values directly. So let's go ahead and do that. What we'll do is we'll say we'll lift the code that's right, so we put it in comment. We'll lift the code from the file, which is, I mean, I say code, but it's really just the virtual alloc that I care about. And we'll go ahead and say that we want a memory size of 512, because remember that's how big sectors are on the hard drive when the BIOS is loading. So we want to do that. So that's going to grab us some memory. And I think that we're going to have to do this before we do this work here. Because then what we should be able to do is we can keep a I guess we'll call it memory index for now. And we'll just say, hey, we're at 0. Wow, my finger's off tonight. And then here what we can do is we can say output.memory at memory index. And I think if I increment afterwards, I think that's going to move it along after it's written to it at the current location. And then we can just say value. There, we can get rid of that. So I think that works. Let's try. So if we load up that file in HXC, we can see that it didn't work, which is a shame. So the other thing we need to do here is we need to add that length to ats for the next time. You know, I'm not real sure why that didn't work, so let's go ahead and tell Visual Studio we'd like to use it. And we can step through here and try to figure out why that's not writing. Seems like it should. Oh, I see. I copied too much. So we don't want to write the file right yet. We want to do it down there. So let's double check. Yeah, okay. I just copied too much. I bet you that works fine. Oop, I didn't want to do that. Hey, there we go. All right, let's close down Visual Studio. Let's give it a rest. So there's our E9, which is what we figured out would be in decimal. So if I go back to our input file and I undo that deletion and I rerun the assembler now, right, we're still outputting the whole contents. But you can see now that we've produced the binary file that we wanted. So this is identical now to the by hand, but instead of manipulating binary values by hand, we've done it by handwriting the assembly code. So that's, you know, one step in the right direction, but it still is a little quirky. We're using decimal values and getting, you know, what we care about is the hexadecimal values on the output, but we're inputting them as decimal values. So that takes an extra thought of translating it between the two numbering systems. And then the other problem is that we have, you know, this large amount of zeros that make it really hard to see what's going on. So let's address these one by one. Let's fix the, let's enhance our detection here to work with hexadecimal values. So I'm going to go ahead and go back to just a simple example. Actually, I'm not. I'm going to go ahead and change these now to be this way, FD and FF. FD, FF, and then this is 55 and AA. Oop. So I'm going to go ahead and do that, and then what we'll do is we'll trim it down to one value, and that way we'll just have to work with that directly. So I'm going to do a couple other things. I'm going to, well, I guess for right now I don't need to remove that print line. And if we run it, there we go. We get just the the first value. So if you notice, what I did when we switched to hexadecimal is I prefixed the number with 0x. So I'm going to use that as an indicator to tell the assembler, hey, the value you're going to end up with is a hexadecimal value. So we're still going to read db's space, but at that point we're going to need to do something different based on whether or not it's prefixed with a 0x. So that's going to occur right here. So what we're going to do is we're going to say, okay, if that value, first value that we're at is 0, and the second value that we're at is an x, we're going to do some hexadecimal processing. Otherwise, we are I'm going to set value outside of this. Otherwise, we're going to rely on our decimal calculations. So there's a couple things that we could do here. We want something similar to this. Except the value this time is going to be 16, I think. We'll find out. The issue here is that instead of doing the simple trick where we can just offset the ASCII value by the ASCII value of 0, we have to take into consideration that we have alpha characters now. We have A through F, and they can be uppercase or lowercase. We probably want to support both, even though I'll probably only ever use uppercase. You might as well just put in the extra little effort there to make it so that it can do either. And we'll test that out. So actually, I think this is going to be pretty easy. We're just going to say if the value that you're currently at is greater than or equal to 0, and the value that you're currently at is less than or equal to 9, then we have the decimal case. Otherwise, if it is capital A, capital F, we do that. If it's lowercase a to lowercase f, we do that. So that should work fine. Now, the other thing is that well, let's give this a shot. Let's see if this works. So that didn't. That gave us 49 when we really wanted E9. So why do we think that happened? That's a great question, and it's not really being obvious to me. So let's go ahead and fire up the debugger and we'll see. So we need to remember to update our output. We want it to go to output bin. And away we go. So I'm going to go ahead and I'll just go ahead and drop down in here. And what we'll do is we have value, or we have results, but we want value. and we probably want to know what at is. Oh, okay, yeah, I saw that and I forgot to fix it. So we checked to see that it starts with 0x, but we didn't do anything based on that. So we then try to parse 0, then we try to parse x, which didn't work. Or, you know, it's not covered in our case. And then when we move to E, well, no, because it was, I'm not sure. That's actually kind of odd. Oops. I have to stop doing that. Yeah, that still didn't work. All right, well, that's fine. That was a mistake anyways. We don't want to deal with the 0x. We just want to say, oh, okay, that's the indicator, throw it away and move on. So let's go ahead and see what actually happens here. So we multiply 0 by 16, of course that's 0. What I'll also do is I'll say at I. So we are going to try and parse the E. So the value we get is 4. Okay, I know what the problem is. So that is right. E is 4 away from A. 4 away from A. What we forgot to do was we switch over to A, B, C, D, E, F. Should be 10 in there. So what we'll do is we'll say plus 10. That'll work. We'll do that. There we go. Now we have EF. So let's go ahead and do the full thing. So there we go. So now we're writing in hexadecimal. And you know, I'm kind of bad about this. I forgot to kind of make commits as we go. So let's back out some changes. I think that's good. What we can say here is that's good. And what we'll say is basic parsing of dB with decimals. Okay, we'll add back all our changes. Now we can say man, that always looks wrong when I write it, but it's correct. So there we go. Okay, so the last thing that we want to do is it'd be nice to get rid of these dB zeros. And if I remember right, we should have 506 of them. So we want to introduce something else that's common in a lot of assembly language, which is the, you can say times, and then a number, and then it will it will repeat that command 507 times. So if we do this, I actually don't know what's going to happen. It's going to not care about the times. The 507, it's actually probably not going to care about either. So let's go ahead and run this because it's kind of interesting to know. Yeah, so that's what I thought. So it just ignores the times completely. You notice our boot records right here at the top. So that's actually pretty simple to do. You can see that we kind of have a little bit, I guess you could call it a structure here, where going. And again, this is just as badly as you can write it for right now. We'll deal with getting this better down the road. So, oops, what I'm going to do is I'm just going to go ahead and fill this out so that it could be times oops, to that, paste, paste, paste. I think that's right. Oh, I see what happened. Okay, I got it. I am 3 4 S and 5. Okay, so if we see it times, we're going to basically want to do the same thing. We know how to parse both hexadecimal and decimals. It might be weird to allow for hexadecimals, but we want to kind of want to do it anyways. Let's hold off because that's a bunch of junky code. So we'll do that. Accept that. Okay, right. So what we need to do is have a way to say, oh, we want you to do this so many times now, after we figure out what that is. So, and maybe instead of having that, what we'll have is we'll say times, and that'll be times, that'll be times, and then, so what we're going to do is we're going to, because times is a prefix to the command that we're going to give. So what we'll do is we'll just capture that in the times variable, and then when we go to do the output, here, we'll just say, well, times is greater than 0. You also want to decrement times, so maybe what we'll do is we'll do a for loop, and we'll say that, and we'll say max times, But then what we need to do here is say it has to happen at least once, because we want to be able to output the if it's just a dB. So the other thing is that I want to think through this here real quick. The at's going to be all of that, but what we didn't do is we didn't capture. We need this basically. And we want that there. So we're going to now move, instead of 3, we're going to move 6. Start the length, figure out how long that's going to be. So now this, instead of looking for the return, the carriage return, what we want to do is we want to look for a space. This is going to be times some number and then the command that we want to do. And we want that command to be picked up by this dB piece here. So I think that that should work. And it looks like it didn't. So that could be, okay, that's because the times is not getting carried over at the ends, because we'll parse the times, we'll come back to the top of the while loop, and then times has been obliterated and reset back to 1. So that's not quite working out how I wanted it to. So let's figure out how we can get around that. I think if we set that outside of that, and if we say here, we reset it back to 1 for the next time. Man, that's bad. No. Okay. Well, yeah, that's not going to work, because the other problem is that when we go to multiply times here by 10, it's going to turn out to be 100, which we don't want. We could do that by clearing times when we come in here. This is just not turning out how I wanted it at all. So let's think about how we can do this. I want to have an indicator that says I want you to do this so many times. I'm trying to loop it back. What we could do, could be messy and just duplicate all of that dB processing code after we figure out how many times we want to do it. Which is okay, because we'll get to something better eventually. I just don't know if I want to do that right now. Let's do this. Okay, so let's see, we're going to get a dB, and then a times. Oops. Three dBs, and then a time. Come on. One more. go. Here we go. Oh, right, drn, db, rn, times. Oh, well, that helps too. If you can't spell times correctly, it's a little bit of a problem. So that goes to 5, 6, and then that would be 7. Still no. So we can see dbrn, dbrn, dbrn times. Oh my goodness. That's why we were off. There's 2 i's. Oh, okay. That worked a little bit. Not quite as far as I thought that it would. So we want to do that 507 times. For some reason, it only did it halfway. But why would it have only done it halfway? Okay. I don't know. I'm getting a little flustered by this. So let's just go ahead and rip through it. I guess what we want here is we care about times. Oh, okay, it overflowed. Times was, yep, okay, not a problem. Go to it. There we go. So let's just double check this, make sure it works right, and I'll explain what happened. There we go. So what happened was we were only using 8 bits for the times number, and so it wrapped around 255 and started back over at 0. I don't know why I took that long to think about it. Anyway, so I think that's pretty good. So we now have a very clean, simplified input. We're getting back the exact output that we want, which matches our by hand example. And we can even throw that into QEMU, however you say that. And if I give it our output binary, we can see there it booted and it's looping there perfectly fine. trouble. There we go. So I think that's good for tonight. Let's wrap up our commits. So, oh, that looks good. And we'll say what we did is allow for DB commands to there we go. So I think that's going to be it for tonight, and I hope to see you guys next time.